喂，可以听到吗？
可以。
对，OK，好，OK。So let's continue. Okay. So yeah, I think I may just as well use like a textbook this part. I mean for the proof. Okay. So any set of unlinear independent vectors spans V. Okay. So say V1 to Vn are linearly independent. Okay. And V is any vector. Okay. So we know like according to our previous uh, um, um, theorem. Okay, uh, uh, because we already know V is a dimension n, right? So there exists a basis, okay, of V that is independent, and also this basis of this n vector in this basis already span V. Okay, and you know then uh, you know, like um, if we consider V1 to Vn and this V, okay, this this thing, we consider the solution of C1 V1 plus C2 V2 blah 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 plus Cn Vn plus Cn plus one V equal to zero. We consider this like a equation. Okay, first, okay, Cn plus one. I mean V. Okay, this Cn plus one. This equation, exists a non-all zero solution, right? Because we have like a n plus one vectors here, right? And previous, you know, uh, uh, um, theorem told us you know, um, if we already have a spanning set of n vectors, the other spanning set cannot be, with more than n vectors, cannot be independent, right? So it cannot be independent. That means like a C1 to Cn plus one. There exists a non-trivial solution, right? And we know this Cn plus one cannot be zero. Why? Because we know V1 to Vn are linearly independent, right? So if Cn plus one is zero, then that implies, V1 to Vn, they are linearly dependent, which is which contradict to the given assumption, any set of unlinear independent vectors. Okay. So in other words, first, Cn plus one is non-zero, and then there exists a non-trivial solution here, and Cn plus one is non-zero. So because of that, so you can move all the term, V1 to Vn to the right hand side and divide both sides by Cn plus one. Then you get a form of this thing, right? V equal to alpha 1 V1 plus alpha 2 V2 plus blah, blah, blah plus alpha n V1, where alpha 1 actually is negative C1 divided by Cn plus 1. Alpha 2 is negative C2 divided by Cn plus 1, and so on. Okay, so in other words, this is remember here we just randomly select arbitrary select a non-zero vector from the vector space V. Okay, so in other words, any vector in vector space V can be spanned by V1 to Vn. Okay, so that's the first one. Okay, the second one, any n vector that spans vectors that span V are linearly independent. Okay, so we already know like V1 to Vn span V. Okay, and the V1 to Vn, we want to show that the V1 to Vn are linearly independent. So here we try to prove this by contradiction. Okay, if V1 to Vn are linearly dependent, okay, if V1 to Vn are linearly dependent, then one of Vi's, okay, for example, I mean, without loss of generality, say the last one. If it's not last one, we just change the index to make it the last one. Okay, this Vn can be written as a linear combination of the others. Okay, so in other words, we can sort of like reduce this spanning set by at least one vector, right? So V1 to Vn minus one span V. Okay, and then if they are linearly dependent, then we continue this process until we find some at one point. Okay, we have a smaller set that span V, and also it is independent. Okay, we can keep doing this process. Removing the vector one by one, and then still be able to span like all of the and and then at one point, because it's already dependent, right? So think about this. Now you have say like let's say we get rid of three vectors. So now we have like n minus 3 number of vectors that span the and they are linearly dependent, linearly independent. Okay, that means what? That means our dimension is n minus 3, right? The dimension of V is n minus 3. But this contradicts to the fact that V is a vector space of dimension n. We previously, I mean, we are given V is a dimension n already, right? So here, like if you use this process to get rid of like some vectors and argue like oh, its dimension is lower than n, there's a contradiction. So in other words, this process cannot happen. So the only place that stop this process from happening is V1 to Vn R has to be linearly independent. Otherwise, we can at least do this trick for one round and reduce like the set by one vector. Okay, so that's it. Okay, so we can show that V1 to Vn, if they span V, then they are linearly independent. Okay, so then let's go back. Okay. So prove that. Okay. So the next theorem is if V is a vector space of dimension n, then first, no set of less than n vectors can span D. Okay. The first one is a given. Why? Because like if there's a set less than n that can span D, okay, we use a similar argument, okay, that we did previously. I mean, if they are independent, then, well, the dimension is less than n, right? We have issue. If they are not independent, then we sort of like can reduce this spanning set by one vector, and then still be able to span the V. Okay, and then we check the independence, whether or not the rest of these vectors are independent. If they are independent, then again we have a dimension like a lower than n, okay, and so on. So we keep doing that. I mean, until we you know we must be able to find like at a point like you know the dimension of your the v dimension is less than n, but it's not possible. So in other words, no set of less than n vectors can span v. Okay, so this is like what we have. And any subset of less than n linearly independent vectors, okay, can be extended to form a basis for v. What does that mean? Okay, this is something like this. Okay, if it has less than n vectors and they are linearly independent, okay. First, we know like they cannot span v, right? If they can span v, then again we have an issue because like that means the dimension of this space v is less than n, right? Okay. So in other words, like since they do not span v, then there must be some vector in v that cannot be spanned by these vectors, right? So let's say a vector v, okay, to be that vector, okay. Then we include this vector in this set, okay, because this vector cannot be spanned by these vectors. So if then we include this vector in here, okay, there must be this you know the original set plus this one additional vector. They must be linearly independent as well, right? If not, then this new vector is able to be you know obtained by the linear combination of the previous vectors, right? So then we extend this independent set, okay, the set of linear independent vectors by one more vector, right? And then you know we check like if we can span v. If not, we keep doing that. We can keep adding a vector until when? Until at the time when this set has n vectors. At that time, we guarantee that okay, these vectors must be able to span v because you know from the previous like theorem. Okay, any set of n linearly independent vectors span v, right? So the second one is done. The third one is interesting. Any spanning set containing more than n vectors can be pared down to form a basis for v. Okay. Pared down just means like reduce. Okay. So say we have like n vectors in this spanning set. Okay, that span v, but n greater than n greater than n, and then in this case, this set of vectors cannot be linearly independent, right? Otherwise, the dimension of v will be m, not n, where m is greater than n, right? Okay, so you know, then because they are linearly independent, okay. So in other words, like we have a1 v1 plus a2 v2 plus blah 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 plus am vm equal to 0. This formula has a non-trivial solution, right? So let's say, without loss of generality, let's say like am vm, that am is is non-zero. Okay, so in other words, you can sort of like represent Vm by a linear combination of the other vectors, right? So so then you can get rid of Vm and still be able to use the rest of like V1, V2, blah, blah, to Vn minus 1. These n minus 1 vectors to span V, right? Okay, so this argument can continue until what? Until this spanning set contains exactly n vectors. At that time, this n vector must be linearly independent according to the theorem that we proved earlier. Okay, so this is the process. We can basically like if we have a spanning set greater than n, we can sort of like get rid of some of them to form a basis for V. Okay. So we have shown these theorems. Okay, so we are done with like this section. Okay. Then the next section is change of basis. Okay. Okay. So so for a given basis, okay, here, okay, we have to make sure like this is an ordered basis. In other words, when we consider this basis, the vectors in this basis are, are like a fixed order. Okay. So well, supposedly, so if V1 to Vn is a basis, of course, like a V2, V1, V3, blah, 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 you change the order, it is still a basis. But now, let's assume the order is fixed. Okay, if it's different, if the order is different, we consider it's the different basis. Okay. Okay. So any vector u in V can be expressed as a unique linear combination of the basis. Okay, so this is important. Unique linear combination. Okay. So to prove that, okay, if not, let me write it. This one probably is easier. So let's say like A1 V1 plus A2 V2 plus plus AN Vn, okay, equal to say we have a vector. Okay, I mean let's prove by contradiction. Okay, so assume we have a vector that can be written like this, and it has another way to write it. Another way to write it. So V can be written as B1 V1 plus B2 V2 plus plus Bn Vn. Okay. So I mean, so the same vector V can be written in two different like linear combination of these n vectors. Okay, where V1 where, and this V1 V2 they are fixed order. Okay, then you subtract the top formula, I mean to the second the lower formula. What you are going to get is 0 equal to A1 minus B1 V1 plus A2 minus B2 V2 plus da 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 plus AN minus BN VN, right? And if they are different, that means like this A1 minus B1, A2 minus B2, blah blah blah, blah AN minus BN. These n pairs, some of them are not zero, right? Some of them are not zero. That means what? That means V1 to Vn are not independent. Is that right? Because we have found a solution, okay, to give like for like like alpha 1 v1 plus alpha 2 v2 blah, 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 plus alpha n vn equal to 0. We have found a solution for this alpha 1, alpha 2 to alpha n that are not all 0. Okay, if that's a situation, we know that this is linearly dependent, right? But we know this is not right because like v1 to vn is the basis of a vector space. So in other words, they should be linearly independent, right? So from this thing, we know like any vector sorry, I should have written this v as a u. Okay, any vector u in V can be expressed as a unique linear combination of the bases. Okay? And then, okay, assume u equal to C1 V1 plus C2 V2 blah, 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 plus Cn Vn, and the order of the V1 V2 Vn is fixed. Okay, we assume this order is fixed. Then C1 comma C2 blah, 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 comma Cn transpose. Okay, be careful with this B. Okay, this B means this for this basis is shorthanded for the linear combination blah, 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 and called as the coordinate vector of U with respect to the ordered basis B. Okay, let me get rid of. So this C1, C2, blah, blah, Cn, is called the basis. But the basis is, has to be, with respect to a certain basis, obviously. Okay, and let's show some examples. Okay, B1 to be 101, 1, negative 1, 0, and the 0, 0, 1. This is first basis. The second basis is 1, 2, 1, 0, negative 1, 0, and the 0, 0, 1. Okay, so these two are the basis. Of course, like you have to show that they are really the basis for R3. Okay, to do that, you need to show they are linearly independent. Okay, and because R3, right? They have 3 vectors. So once you show they are linearly independent, they must be they must span like R3. Okay, but let's assume they are linearly independent. Because if we are doing the lecture like in the classroom, I would have like done that. Okay, for you. Okay, but anyway, okay, like assume B1, okay, is like that, B2 is like that, and consider the vector 1, 1, 1. 1, 1, 1. This is also like with respect to certain basis, right? But if you do not write anything, okay, we assume this is with respect to the standard basis. What is standard basis? 100, 010, 010, right? I mean, that's the standard basis, right? Okay, so this 111, because 111, okay, can be written as 2 times this one plus -1 times the second one plus -1 times the third one. Okay, so and these 3 are are from the first base, right? From the first basis. So we know like this 111, okay, with respect to the standard basis has coordinate 2, -1, -1. Okay, I mean, you have to put the B1 here. Okay, if you don't put B1 here, I mean, the answer is wrong. Okay, and also the same vector can be expressed, as 1 times 1 to 1 plus 1 times 0, -1, 0 plus 0 times 0, 0, 1. Okay, so it has also another coordinate. Okay, 1, 1, 0. Okay, B2. Okay, and non-zero vectors have different coordinate vectors with respect to different bases. So if the basis is different, their coordinate will be different. Okay, I mean, you can easily see that, I mean, through this example. Okay, so I know like I mean, because we are not in the class, so this is like we cannot like write it on the blackboard to show like a computation, like intermediate computation. But I mean, just want you guys to understand. Okay, this type of computation is the we are going to do this type of computation like regularly, like in this class, like for quiz or like for like midterm. Okay, keep in mind quiz and the midterm are coming up. Okay, very soon, right? Okay, next week, well, next time. Okay, the week after next we'll have quiz, and the following week we have like a midterm. Okay. And then, okay, here is the like how we can change the code what should I say, like for one vector, how do we change the basis from one base to another one. I mean, of course, when you change the basis, the coordinate will change as well. Okay, so how do we do that? So let's say B1 is V1 to Vn, B2 is U1 to Un. Okay, there are 2 bases for V, okay, for vector space V. So if the coordinate vector of W with respect to B1 is C1 to Cn, okay, of course we write B1 there. And the coordinate of vector of W with respect to B2 is D1 to Dn, okay, and B2. Okay, there are certain, connections between like C1 to Cn and D1 to Dn. Okay, what's their relationship? Okay, so we know like because for if the coordinate for B2 is D1 to Dn, like V, what should I say? Well, before we talk about that, because they are they are both spaces, right? So we can represent Vi as like a linear combinations of Ui, right? So Vi equal to A1iU1 plus A2iU2 plus blah 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 ANiUN. this is a little bit special. This is 1i, 2i, ni. Okay. So if we have that, so when we consider W equal to Ci, so C1 V1 plus C2 V2, blah, 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 plus Cn Vn, okay. This is the meaning of like this W can be written as like C1 to Cn B1, right? So W is a linear combination of like is C1 V1 plus this one. Okay, and then because we know V1 can be written as linear combination of the UIs, so it's written like this. C2, sorry, V2 is like this, and so on. Okay, and then we try to rearrange that because like each of these has a U1, right? So we put the U1 together, it becomes like this. We put, I mean, every term here has a U2. We put U2 here, it becomes this, and so on. So what does that mean? That means this is D1, right? This is D1. This is D2. This is Dn, right? Right? So actually, you can try to represent it as like a form of matrix. Okay, D1 to Dn equal to A11 A this row times this column. That's D1. That's this one. Okay, the second row times this column is D2 and so on. Okay, so this is like what we have, and we call this this matrix as B1 to B2, B1 to B2, because we represent every here we represent every vector in the first base as a linear combination of the second base, and this is 1 2. This is V1 is like A11, A21, and A31, and so on. So actually, that's like that's the coordinate of the V1 in terms of the second base. This is the coordinate of V2, okay, in terms of second base, and so on. So it's column vectors, okay? So this is B1 to B2. And obviously, I mean, the other direction also apply. So C1 blah blah Cn, okay, B1, okay, equal to this one, B2 to B1, okay, like A1 to AN. Okay. And one thing interesting here is that, okay, obviously, okay, this D1 to Dn B2 is this one, right? As we know previous. And we know this one, according to this one, is here, right? Is this one. And so that means what? That means this one, this matrix times this matrix is going to be identity matrix because this vector and this vector, they are the same. Okay, not only they are the same, I mean, this D1, D2, blah, blah, to Dn, they can be arbitrary value. Okay, so the only possibility is this multiplication of these two matrices has to be like an identity matrix. Okay, in other words, these two like a transformation matrices, they are inverse to each other. Okay, so let's take a look at some example. Actually, this is like the basis that we used earlier. This one. Okay. 101, 1 negative 1 0 0 0 1, and 1 2 1 0 0 negative 1 0 0 0 1. Okay. So we used these two bases earlier already. So we have this one equal to this one equal to this one, right? Like we know that already previously. And we can represent the first basis, the vectors in first basis, as like the linear combination of the second base, the second basis. Okay, so you see 101 can be written as 1 times 121 plus 2 times 0 negative 2, sorry, negative 1 0 plus 0 times 0 0 1. So the coordinate for 101 is 1 2 and 0. And coordinate for the second vector in base 1 is 1 negative 1 0. Okay, that's 1 times 1 2 1 plus 3 times 0 negative 1 0 plus negative 1 times 0 0 1. So the coordinate for the 1 negative 1 0, okay, in the second basis is 1 3 negative 1. And 0 0 1 is going to be 0 times the first vector plus 0 times second vector plus, well, because they are the same, okay, the third vectors are the same. So the coordinate will be 0 0 1. So you see 1 2 0 1 3 negative 1 0 0 1. So it's 1 2 0 1 3 negative 1 0 0 1. So this is what? This is B1 to B2. This is B1 to B2. And we can verify, okay, this one multiply the, 2 negative 1 negative 1, that's the basis of B1. Sorry, the coordinate of this vector in B1. Okay, if you multiply this one, you get this 1 1 0. That's the coordinate of the same vector in base 2. Okay, and then similarly, okay, you can represent the second base, the vectors in the second base, as using the linear combination of the first base. 1 2 1 is 3 times the first vector plus negative 2 times second vector plus negative 2 times third vector. And 0 negative 1 0 is 0 negative 1 times the first vector plus 1 times the second vector plus 1 times the third vector. And 0 0 1 is it's a 0 and 0 times the first and second vectors plus 1 times the third vector. So you see the B2 to B1 is like a 3 negative 2 negative 2 3 negative 2 negative 2. The first column is this. The second column is negative 1 1 1 negative 1 1 1. The third column is 0 0 1 0 0 1. And if you put like this is B2 to B1, right? So you put the coordinate of the B2 here, 1 1 0, multiply this one, you get 2 negative 1 negative 1, which is the coordinate of the vector of this vector in B1. Okay, and obviously these two vectors, if you multiply together, you get like an identity matrix. In other words, this matrix and this matrix, they are inverse to each other. You can give it a shot. Okay. So we are done with the like a change of the coordinates. Okay, and this thing is very important, like in practice. Okay, change of coordinate is something we use in in practice very often. Okay, because for example, okay, how should I say uh a lot of time for example you have um you read some input from sensors, right? In practice, for example, if you have some sensors and you read the input from the sensor, for example, it's acceleration acceleration sensor 就是那个加速器啊，加速的那个感测器。Okay, so it will tell you the the um the vector or the vector of the acceleration, right? Where this this thing is accelerated. Okay, 就是说你把那感测器放到一个东西上，你去侦测它的那个加速度好了。OK，那譬如说你把感测器放在随便讲，放在一个球上，放在一个子弹上面，放在一个这个飞弹上面，OK，你要去侦测它的加速度，OK，就是 a moving object，put it on the moving object，OK，so you can read its acceleration，OK，in terms of the coordinate of that particular sensor, right? 因为这个加速度的的衡量，一定是 based on 那个感测器的就是那个它的那个 coordinate 嘛，对不对？感测器怎么装，比如它的方向性是怎么样子，它就是那个方向，对不对？So coordinate, okay, may keep changing, okay, when the object is moving. Okay, but but I mean for we engineers, okay, we observe this the moving object through from a fixed point, right? 就是我们在观察这个移动的物体的时候，其实我们的位置是you could say it's Earth coordinate, right? 这是地球的那个 coordinate。Right? So the coordinate you read from the sensor is different from the coordinate you have at your own position. So you have to do this coordinate change in order to understand where this object is accelerated to, right? 你必须要知道怎么样子换这个 coordinate， 才知道说这个物品这个 object 是往哪边加速嘛？对 ，so I just want to tell you, okay, although compared to the previous section, this section, okay, the coordinate change really is a short section. However, I would have said that I would say that okay, this section perhaps is one of the most important sections in this class. 就最实际上有用处的这个 section 哦，就是跨很多领域的。OK，这个在线性代数最有用的，其实就是这一节。OK。Okay, so let's continue. So row space and the column space. Previously, we were mostly talk about like square matrices. Okay, but this one we are talking about the matrix we are talking about are not necessarily square. OK， 就是前面我们讲都是比较是方形的矩阵，大多数的情形是方形矩阵为主啦。OK， 但是这边我们讨论的就不一定是方形矩阵啊，不一定。OK， so if A is an n times n matrix, then the space of R1 times n spanned by row vectors A1, A2 to Am. We have n row vectors, right? Okay, these row vectors span a subspace called row space of A. Okay, and similarly, if you consider the column vectors, okay, A1, A2 to AN, be very careful, okay? Notation wise, okay, when we, even though this are all the AIs, okay, the row vector, okay, I mean, the index is at the top. So A1, A2, AM, okay, they are in the upper corner. But the column vector, okay, A1, A2, they also read as A1, A2 to AN, okay, but their index appear in the lower corner. Okay, so this is a row vector, this is the column vectors. Okay, so these column vectors also span a space, a subspace, right? So this column vector, okay, the space spanned by the column vectors is called the column space of A. Okay, so we have this row space of A, we have column space of A. Okay, be very careful. They are, you know, not only they are different, their dimension, I mean, well, the number of elements is also different. Okay, their shape is different. Okay, so you see like this row space is like R1 to N. Column vector is Rm. Okay, because it's a column space with what should I say, like a vector elements. Okay, but this one is like the row space is like lying down. Okay, with n elements. Okay, so they look different. They have different number of elements. You know, so they are very different. But they have something in common, as we will point out in this section. If A and B are row equivalent matrices, then the row space of A is the same as row space of B. Okay, so if you know, remember like a row operation. Okay, row equivalent means like B can be, you know, obtained from A by elementary row operations. Okay, so what is elementary row operation? Do you guys still remember? The first one, swapping like two rows, right? The second one is like multiply one row by a non-zero scalar, right? The third one is multiply a row by a scalar and add to the other row, right? These three operations are what we considered elementary row operations. But keep in mind, this elementary row operation, these three elementary row operations, they can all be undone by elementary row operations, right? 就是这些 elementary row operations， 这些三个我们前面讨论的 elementary row operation， 他们可以用 elementary row operation 类似 elementary row operation 把它复原回去，对不对？ And also these elementary row operations are kind of like linear combination of some row vectors, right? So having said that, okay, because they can be undone by the similar row operations, elementary row operations. So this elementary row operation does not affect the row space of a matrix. Okay, so row space of a matrix remains the same. Okay, after the elementary row operations. Okay. So the next one, if A and B are row equivalent matrices, then a given set of column vectors of A is linearly independent, and only if the corresponding columns of B are linearly independent. Okay. And a given set of column vectors of A is a basis of the column space of A, if only if the corresponding column of B are a basis of the column space of B. Okay, so now we are talking about like the connections between row equivalent matrices and the column space. Okay, so it is very interesting because like we are doing like a row elementary row operations, but we are talking about column space. Okay, the important thing is like this. Okay, AX equal to 0 and BX equal to 0 are equivalent. What does that mean? Here, okay, we are trying to do you guys still remember like at the very beginning, why do we need to introduce elementary row operations? 我们在刚开始的时候，为什么要讨论 elementary row operation？ 大家还记得吗？是第一章吧，还是第二章？我有点忘了。对，是因为要解线性方程组，对不对？对不对？也就是说，你在做 elementary row operations 的时候，它不会影响到你的解嘛，对不对？你的解还是一样嘛。也就是说，你 ax 等于0跟 bx 等于0，我们之前讲的 equivalent 指的是说它的解空间是一样的，就是那个 x 是一样的。就是你在解这个线性联立方程组的时候，我们that's a part of the Gaussian Jordan elimination, right? Gaussian elimination, right? So this x1a plus x2a x1a1 plus x2a blah blah plus x and a n equal to 0 and x1 b1 blah blah blah. They have exactly the same solution. What does that mean? First, What is A1, A2, or AN? Be very careful. This is like a lower corner, right? 这个 A1, A2 它代表的是 column vector 哦，就是 大 A 的这个 column vector。这个就是开始这个我在很早的时候有讲过这个等我一下啊，我把那个找出来。Give me one sec. 嗯 Do you remember this slide? This is a system of linear equations, right? 这个是那个线性方程组嘛，对不对？那我们那时候大多数的时候，我们都在强调的是右下边这个，对不对？The matrix formulation. But I told you at that time, remember the left hand side. 记得左下边的这个东西，就是这个147258369 What are they? They are the column vectors of this matrix, right? 对不对 Okay. So at that time, okay, we talk about this. Okay. So this thing finally come in handy. OK，终于我们会用到这个东西了。OK，就是在这个讨论 column vector 的时候，OK，等一下哦，这个跟这个 has the same solution. This and this have the same solution. Okay, I mean when I say have the same solution, I mean like x1, x2. This x1, x2, they have the same solution because they represent pretty much the equivalent system of linear equations, right? 那当你用这个东西去考虑的时候，它其实就是代表了上面讲的这个东西。A given set of column vectors of A is linearly independent if and only if the corresponding columns of B are linearly independent. A given set of column vectors of A is a basis of the column space of A if and only if the corresponding columns of B are basis of the column space of B. Okay. But here, okay, one thing I have to make sure, okay, you guys notice is that, okay, did I ever mention the column space of A? I mean, I know that A, B are row equivalent matrices. Did I mention the column space of A and the current space of B are the same? No. They are different. I mean, they may be different. They may be different. Okay. I'm just saying, okay, if a given set of current vector of A, if they are linearly independent, then the corresponding currents in B, they are also linearly independent. Okay, but I never say A and B, their current space are the same. No. These are two different things, right? 就他们的 current space A 和 B current space 可以不一样，但是这两件事是有关系的，就是他们的 current vector 之间是有关联性的。这边要很小心哦。So for any matrix, the dimension of its row space is the same as the dimension of its current space. Okay. What does that mean? Okay. First, you reduce a matrix into a row echelon form. Okay. It will look like, what does it look like? You will see like, some of the, 不知道怎么讲。When you reduce a matrix to row echelon form, some rows at the bottom may be all zero, right? Some rows in the bottom may be all zero. And above that, okay, those are, what should I say, like they're like non-zero rows. And those non-zero rows has leading one, right? And with those leading one, if you want, you can, I mean, further do something to eliminate like the top non-zero elements. So in other words, like they are guaranteed to be linearly independent. Those like those row space must be generated by those row vectors, right? But how about the current space? When I say leading one, okay, because I say like it can the lower rows are empty, and the top row, as I say, you can get rid of the non-zero ones. Okay, so 这个就是它是这个它是长这个样子嘛？可能这边是一，这边都是零，对不对？下面都是零啊，这边是一个一，下面都是零。OK，然后我随便写哦，这边是一个一，然后这边下面都是零，这边都是零。我在这个特别的例子里面，它的 row，它的那个row dimension，它这个 dimension 这个 row 的 dimension 是不是因为这个跟这个注意哦，这边这都是零哦，这边都是零，这边都是零。那这边的话，上面也是零，下面也是零，这边是上面都是零。那这边当然有一些不是零的哦，这边下面有一些不是零，但是重点是 ，if you look at this， okay, their row space is spanned by this non-zero rows, right? 所以，譬如说，在这个地方，当然就是这个。假设我这边就画3个好了，就是这它 dimension 就是3嘛。Dimension in this particular example is 3. Okay, and obviously they are also independent and they span like a row space. Okay, so dimension of row is 3. But if you look at this direction, the column space, so they obviously they also the dimension is the same, right? It's also 3, right? So if you reduce the matrix to row echelon form and with enough discussion, you will find that the dimension of row space and the column space are equivalent. Okay. And because of that, if A is a matrix, the dimension of the row or column space of A, okay, because they are the same, okay, we call this as the rank of A and represent it as rank A. Okay. So now, okay, we are trying to link in the null space with the rank. We will put them together. Okay. If A is an n times n matrix, all solution of AX equal to 0 form a subspace of Rn and is called the null space of A, denoted by null A. This is not new, okay? The first point is not new. We know that from null space discussion. Okay, but the second one is interesting. The dimension of null A is called the nullity of A, denoted by nullity A. Okay, and then if A is an n times n matrix, we have rank A plus nullity A equal to n. Okay. So this one is something new. Okay, rank A plus nullity A equal to n. First, what is n? N is number of columns, right? N is number of columns. And it also means like, the number of unknown, the number of unknown in AX equal to 0. In AX equal to 0, that X, the number of unknown in X. Okay. So here it means like, or if I try to write it as like a reduced row echelon form, like you see this, and this is your X. This is X1. This is Xn. Okay. Okay. And then, okay. Look at here. Okay. The ones that you have the value ones, leading ones. Okay, I previously told you that the number of the rows with leading ones will be the dimension of your row space, or put another way, the rank A, right? And those sort of like I mean, if you consider this as like as a I mean, when you are trying to solve this system of linear equation, those are like confined, confined the first few like unknowns, first few like xi's, and those like with zeros, those few the bottom zero rows will be corresponding to this the last few xi's. Okay, and those xi's represent this nullity A, right? It represents like how many like I mean the dimension of your null space, pretty much. Okay, so the top like the what should I say, like the leading one, the number of leading ones is your rank, and the bottom, the number of like zeros, okay, will be the will represent like the dimension of the null space, which is nullity, and they add up, okay, to be the number of like unknowns in your like system of linear equation, which is n. Okay, so that is why the rank A plus nullity A equal to n. Okay. So if AX0 is a solution of AX equal to B, then the solution set AX equal to B is X0 plus X prime, AX prime equal to 0. Okay. Here, X0 is a particular solution. Okay. One particular solution for this one. Okay. So this one is relatively easy to show. Okay. For any X prime, okay, such as AX prime equal to 0, X0 plus X prime obviously is a solution AX equal to B, because you multiply A on the left hand side of X0 plus X. The first one, I mean, you use like a distributed law 分配率，那这个 A times 刮弧 parenthesis A X0 plus X prime. The first, I mean, you expand it. I mean, you get AX0 plus AX prime. So AX0 give you B, right? The AX prime give you, 0. So B plus 0 is B. So any X prime, in this null space, okay, it'll give you like X prime, X0 plus X prime is a solution. So for any X double prime such that AX double prime equal to B, we have to, because this is if only if, okay. So we need to show like the solution, any solution can be written like as any solution of AX equal to B can be written as X0 plus X. Okay, so now, so the other direction, X double prime, AX double prime equal to B, we just let X prime equal to X double prime minus X0. Then we know X prime, AX prime, so we multiply A on the left hand side of X prime equal to A times this one. And we use distributed law, okay, 把它乘进去，这边 A double X double prime 减掉 A X0，AX double prime 是 B， 那 AX0 is B，so B minus B is 0。所以呢 AX prime 是在这个，我们如果让这个东西 当 x prime 等于这个的话，这个就是在这个ax prime 等于 b 这里面。Okay, so this is the proof of this theorem. Okay. Yeah. Okay. Okay. So ax equal to b is consistent. Okay, if and only if rank A equal to rank A column B. Okay. First, what is consistent? It means there is a solution. Okay, there is a solution to this system of linear equation. Okay. If there's a solution to the system of linear equation, according to how we write it, this thing, this left-hand side, as like as a linear combination of a column space, we can say B is in a column space, right? If this one has a solution, B is in the column space, means B can be written as a linear combination of column vector A, right? Okay. So the dimension of the column space of A, B are the same as that of A. Okay. Because B is a linear combination of A of a column vector of A. Okay, so this is okay. If this is X equal to B has a solution, this rank A equal to rank A column B. Okay, so from left hand side to right hand side is satisfied. Okay. And there's another. Sorry. Sorry. So another direction. Okay, rank A equal to rank A B. This one also means like a B. If you add a B to attach additional column B to this matrix, it does not change the column space. That means what? That means B can be linear combine linear can be obtained by linear combination of the previous columns. Okay, so from the right hand side, we can also get like AX equal to B is consistent. Okay, so both sides, it's like it's okay. So we are done with this chapter. Okay. Well, we still have like 3 minutes, but I think like I guess we'll stop here today. Okay. And next time we will start the next chapter. Okay. And the quiz, okay, will be given, okay, and it will cover up to the end of this chapter, by the way, okay? And I will give you the practice question tonight, okay? So any question? If no question, that's it for today. I will see you like the week after next. Okay? Yeah, thank you.